All right. So let's see what we'll need to do to really, this is almost dimensionless, right? We need to multiply by L squared, divide by KEQCA naught, and once we isolate this term, this has no dimension, and we'll be sure that the rest of this equation also has no dimension, because if we're just adding things, they had better have the same units. So, final step here to make this dimensionless, minus L squared K double prime CA all over KQCA naught times diffusion of A through B. All right, so if this is dimensionless, then this should also be dimensionless. And what I said at the beginning is we have this really kind of special number that pops up, and it lets us know if the reaction rate is high enough to use up the species, to react the species by the time we've reached the end of the tank, or if the diffusion is so high that we're reaching the insulated boundary condition where we assumed the concentration was 0, and we sorry, so this is the I'm trying to like be kind of creative to approach this. This is a Damn-Kohler number. Damn-Kohler number tells us whether or not we are reacting our species fast enough, or whether or not we are inhibiting the reaction with the diffusion coefficient. So we can have two possible cases. Let's say we can diffuse really fast in the system. Then we are limited by the reaction rate. If we can increase the reaction rate, then we can have a system where we're reacting all the species by the time it gets to the top, and we're not having a lot of extra accumulation, right? We're talking about if the diffusion is high, then we start at the bottom, we diffuse A all the way to the top before we react it. Or we can react all of A down at the bottom surface if the diffusion coefficient is too small, and then basically any length of reactor that we have above that is meaningless. It's a poor design. So if this number is very low or this number is very high, that's no good. We would like to, in fact, let's write this.